afternoon, or morning. This is Professor Elliott, and this is a overview presentation on the BJT transistor switch. Okay, so this is the first circuit. We're using a base bias and to drive the LED switch. Okay, so over here in figure A, we have an open switch. So obviously if the switch is open, the base current through base resistor RB is 0. If there's no base current, then there cannot be any collector current. So the transistor is off and the LED is off. So in this case, our only function, our purpose, is to illuminate the LED when we close the switch. And if it does that, then it satisfies our operating condition. Notice in circuit A, the LED is in the collector side, while in figure B, it is in the collector side as well, but we've moved the current limiting resistor from the collector side to the emitter. And when we move the resistor to the emitter, we call that RE. E is for emitter, and while it's in the collector, it's RC. C is the collector. Okay, so you can make it work different ways. There's plenty of combinations, depending in applications to NPN, PNP. Do we need to saturate the switch? Is it in the active area, and on and on and on. So, but this is just two very simple examples. Now, in both cases, back to figure A, when we close the switch, then we will forward bias the base to emitter loop, and then the transistor will turn on, and we'll have enough current to illuminate the LED. In figure B, when we close the switch, we have current flowing from the base to the emitter, again, which will then turn on the transistor, and then the LED will illuminate. Now, the real difference between the two circuits is the base bias circuit, which is lab experiment number 4 in the current version, that it's very beta unstable. Okay, so the actual current and collector to emitter voltage varies a lot with the beta, which is a highly unstable value. In figure B is that by putting the resistor in the emitter, now it's called emitter biased. That from the perspective of the base, that emitter resistor gets blown up beta time. So the figure B, the current will be a lot more stable. That's the design side of things, but it can work. Again, this is a basic switch. It can work either way. Okay. So there's my notes and comments. You can have a look through that. Those are all my step-by-step details. Okay, if you want to pause the presentation, take some notes, then please do so. BJT switch at cutoff. Okay, so there's two ends of the DC load line, which is the relationship between collector current IC and collector to emitter voltage VCE. At cutoff, we envision the switch, the transistor being mimicking an open switch, as shown in the illustration there, and therefore the current in the collector is 0, and then all of VCC appears across the collector to emitter terminals. Now, in practice, there is still a little bit of leakage current, so there is a small voltage drop across that collector resistor, which in this illustration they're calling RL for load. So let's just say VCC is 10 volts. Then practically across the resistor, you might have like 0.1, and across the collector emitter, you'd have like 9.9. Ideally, we'd have 0 volts on the resistor and 10 volts on the collector to emitter. So it's all very, very close in practice. At saturation, that's the upper end of the load line. And in this case, we envision the transistor behaving as a perfectly closed switch, and ignoring the dynamic resistance collector to emitter, which you can never make 0. But we're just going to pretend it is. In that case, then VCE is 0, practically fully saturating the transistor. That voltage is going to be, 0.1, 0.2, 0.3, 0.4, somewhere in somewhere in there. The more you saturate the transistor, the longer, the higher the switch, it takes to come in and out of saturation. So it actually reduces the switching speed, which may or may not be an issue. But anyway, there's all my notes. So please feel free to take them down. But anyway, you'll be doing a full lab on BJT switching, which in this current lab version, I believe is lab number 6. NPN, BJT NPN switch. Again, there's lots of different configurations, and I'm not trying to cover them all. But in this case, you can see where I got this nice illustration from. Give them full credit. Is that move that up to there? Is that we're using just an AND gate with a switch to control the input, current limiting resistor, and when you close the switch, so you put a logic 1 at the input of the AND gate, the output, you get a logic 1, showing here's a pulse, forward bias, the base to emitter junction, boom, and turn on the LED. So they're using the BJT to as the interface between the gate and the LED, which I personally really like. There's plenty of different ways to do that, because it allows us to have higher currents. If you're driving the LED directly with the logic gate, depends on the family, but we'll talk about the LS series because that's the one you're using in your digital logic. Is that if you put it in current syncing mode, you can only get up to 8 milliamps, which is enough to turn on the LED. If you want to have it in current sourcing, so you want the LED to be on when the gate output is 1, it's only 400 microamps. That is not enough to drive the LED, but it's plenty to drive the base of the transistor, bias the transistor up in the active area, have lots of current gain, and you get all the LED current that you want. Okay, PNP switch. Again, this is just a different. There's many ways to do this. In this case, then, in order to forward bias the base to emitter junction, the emitter has to be 0.7 volts-ish more positive with respect to the base. So that means the output of the NAND gate needs to be at logic 0. And we're using RB for the current limiting, so that when we close the switch, so that will forward bias the base to emitter junction, and then the light will turn on. Notice that we've moved the emitter down, the LED down to the emitter side. Now in class, we're going to be doing quite a few different examples, as well as the ones that you would do in Lab 6. So we have lots to look at, but there's lots of different combinations. Okay, BJT switching a relay. And this is a very common application. Photo sensors, inductive proximity sensors, etc., are typically transistor type outputs, and you can use them as an input device and use that to drive the base of the transistor. Notice we have a flywheel diode. Notice a polarity across the relay. The relay, remember, is an inductive coil. That flywheel diode is sometimes called a freewheeling or a snubber, and it is there then to protect the transistor When you cut off the base current, you cut off the collector current, that magnetic field has to collapse, that energy needs to go somewhere, and rather than destroying the transistor, it's going to be dissipated through that then forward bias diode. Okay, thanks for watching. Catch you later. Bye-bye.